In this section, we're going to be looking at rational functions. We're going to determine how to identify the domain of rational functions. Then we're going to look at asymptotes. We're going to look at how to identify vertical asymptotes and wholes of rational functions. And we'll also look at how to identify horizontal asymptotes of rational functions. And then we'll also identify rational functions from its graph. So let's first consider determining the domain of rational functions. So first, when we speak of rational functions, we just mean a fraction of polynomial functions where both the numerator and the denominator are polynomials. So let's suppose we have a rational function f of x, then it can be written in terms of two polynomials, p of x and q of x, as the following. So if we have p of x as our numerator, q of x as our denominator, then we can write our polynomial out as what we've seen before, where the leading degree of p of x is p, and the leading degree of q of x is q. So anytime we have a polynomial over a polynomial, we just mean that's a rational function. Now, let's suppose we have a linear function. So we have a rational function that is a linear function in its domain, in its denominator. Then we say the domain must exclude that number that corresponds to the zero of that linear function. So whenever we are speaking of a domain, we want to see what makes the denominator zero. Now, let's review the steps that we would take in order to find the domain of a rational function. So the first key thing you want to do is you want to set your denominator, whatever that polynomial is, set that denominator equal to 0. Then, if possible, we want to factor that denominator and set each factor equal to 0. Then we'll use those factors to find the numbers that make the denominator 0. And then once we do that, the domain will be all real numbers, excluding those values that we found that made the denominator 0. So now let's take a look at this example. Let's suppose we have the function x plus 3 over x squared minus 9, and we want to find the domain of this function. So if you remember, the first key step is to take our denominator and set that equal to 0. Now the next thing is to factor this denominator. So we want to factor x squared minus 9. And so that factors into x plus 3 and x minus 3. Now we want to take each of the factors, set them equal to 0, and determine what's going to make that denominator 0. So now we take each of those factors separately, set them equal to 0, and now we can solve for x. And therefore, we get x to be negative 3 and positive 3. So those will be the two values of x that will make our denominator 0. So, in other words, those are going to be the two values we want to exclude from our domain. So if we think about it this way, we don't want x to be negative 3, and we don't want x to be positive 3. So therefore, we can write our domain this way. The domain will be all real numbers excluding negative 3 and positive 3. So this would be the way in which we could write our domain. So now let's suppose we wanted to analyze that function a little bit more by examining its graph. Well, here we can see that something indeed is happening at negative 3 and something indeed is happening at positive 3. So remember we said the domain was all real numbers except negative 3 and positive 3. Those were the two values that we were excluding. Well, you can see here at negative 3, there looks like there's a hole there in the graph. And then here at positive 3, we have this vertical dotted line here. We consider that to be the vertical asymptote. So we'll later discuss in further details about what we mean by the hole in the graph and vertical asymptote. But this graph here confirms that we want to exclude negative 3 and positive 3 in the domain. Now let's consider another example. Let's suppose we now have this function 4x over 5 times x minus 1 times x minus 5. Well, if you notice, the first step is to always take that denominator and set it equal to 0 and then to factor. Well, if you notice, the denominator is already factored for us. So we're just going to go ahead and take that denominator and set it equal to 0 and solve for x. So when we do that, setting each of our two factors equal to 0, we get x is equal to 1 and positive 5. You'll notice here we just have this coefficient 5 in front. It doesn't have a variable attached to it, so we don't have to worry about setting that equal to 0. So we only get the two values that would make our denominator 0 to be 1 and 5. But remember, we really want to think of it this way. We don't want x to be 1, we don't want x to be positive 5, so our domain will be all real numbers excluding 5 and 1. So therefore, we can write our domain as so, all real numbers excluding 1 and 5. So now let's take a look at how to actually identify those vertical asymptotes and those holes in a graph. So first, when we speak of an asymptote, we just mean that it's an imaginary line that a curve of a graph approaches, but it cannot cross that line. It'll get really, really close to that imaginary line, but it actually never cross over it. And we say this is where the function is actually undefined. So first, if we want to identify the vertical asymptotes, then this is found when using those zeros of your denominator of the rational function. So we'll take whatever polynomial function we have in that denominator, we'll set it equal to 0 and solve for x, or solve for your variable, and that's going to help us determine the zeros where the function is undefined. Then if we want to identify the hole in the graph, well, the hole is just a point on the curve at which the rational function is undefined. So think about if we have an open circle somewhere on that graph, then that's going to let us know that we have a hole there where the function is undefined. We also refer to this hole in the graph as a removable discontinuity, and this is where an asymptote does not occur. So if we have a removable discontinuity, we're just saying we have a hole in the graph, and you can think of it this way, where the hole is being, or a point on the graph is being removed from that graph. So now let's review the steps in identifying the vertical asymptotes and the holes. So the very first thing we want to do is factor both the numerator and the denominator. Then we want to simplify the function by canceling out any common factors that we see in the numerator and the denominator. Then we'll set the denominator equal to 0 and we'll solve for the given variable. Once we solve for that given variable, then that's going to tell us where the denominator is 0. So the vertical asymptotes occur at this value that make the denominator 0. Then we're going to go back and look and see if we had any canceled factors. If so, we'll set those factors equal to 0 and we'll solve for the variable again. Then those values let us know where the hole occurs in the graph. Now let's take a look at this example. So let's suppose we have this function 2x squared plus 5 over 2 minus x squared, and we want to identify the vertical asymptotes. Well, the first thing that we need to do is take our denominator and factor that and set it equal to 0. So you will notice our numerator does not factor. Okay, so there's no way to factor that, so we just rewrite the numerator as is. And now our denominator factors into 2 plus x times 1 minus x. All right, now that we have that factor, we want to take our denominator, set them equal to 0 to determine the value of x that makes the denominator 0. And so we see x is undefined at -2 and +1. So after setting each of our factors in the denominator equal to 0, solve for x, this identifies our vertical asymptote. Well, you'll notice since we weren't able to factor the numerator, we didn't have any common factors that we needed to cancel out. So therefore, we don't have to worry about determining whether we had holes or anything in that nature since we didn't cancel anything. And so therefore, only the vertical asymptote occurs at -2 and +1. So therefore, we can just state that the vertical asymptote occurs at -2 and 1. Now, let's suppose we want to analyze that function a little bit further by observing its graph. So here, this is a graph of this function 2x squared plus 5 over 2 minus x squared. And remember we said that a vertical asymptote occurred at negative 2 and 1. So we can see here that this graph does indeed confirm that we have those vertical asymptotes at those two places. So you can see this blue line represent the graph. We can see that it gets really close to this dotted red line and really close to this dotted orange line. But as it approaches it, it gets close, but it actually never crosses over. So this is how we identify the vertical asymptote when looking at rational functions. Now, let's take a look at this example. We have this rational function x squared minus 1 over x squared minus 2x minus 3. Now we want to identify the vertical asymptote and any corresponding holes. So we know the first step is to always factor the numerator and the denominator. And so therefore we see that the numerator factors into x plus 1 times x minus 1, and the denominator factors into x plus 1 times x minus 3. Well, now we can see that we have a common factor here in the numerator and the denominator. So before we cancel those out, let's go ahead and cancel out those common factors. So now, since we have that common factor, well, we know that's where the hole is going to exist, and then the other factor that's left over, that's going to represent the vertical asymptote. So if we set those two factors in our denominator equal to 0, set this equal to 0 separately, remember that canceled factor corresponds to where the hole exists, and then the other factor that remains, that's going to identify our vertical asymptote. So now let's solve for x for both of them. So therefore, we say we have a hole at negative 1 and a vertical asymptote at positive 3. So therefore, we can state it this way. The vertical asymptote occurs at x equal 3, and then the hole in the graph exists at x equal negative 1. Now let's take a look at the graph of that function. So remember we said there was a vertical asymptote at positive 3 and a hole at negative 1. So if we look at the blue line here, that represents the graph of that function, and we can see there is indeed this dotted red line here at x equal positive 3. And so we can see that the blue line approaches that line. It gets very close to it, but it never is going to cross over. In both directions, we can see that. So this is one place where the graph, where that function is undefined at x equal 3. We also see that there is indeed a hole at x equal negative 1. And so, remember, we can also refer to this as a removable discontinuity. So think about that's where the piece of the graph has been removed at x equal negative 1. And this is also where the graph is undefined. So undefined at the hole at negative 1 and undefined at this vertical asymptote at x equal 3.